What if I told you that a huge part of the AI explosion we're living through right now, I'm talking everything from chatbots to those amazing translation tools, can all be traced back to one single research paper from 2017. It's got this kind of cheeky title, Attention is All You Need. And its core idea, well, it didn't just improve AI, it totally changed the game. Okay, let's dig into this thing. So, for years, AI researchers were banging their heads against this one massive problem. Think about it. How do you teach a computer to really understand context? Not just word by word, but across a whole story. Like if you're translating a super long paragraph, how does the model remember that the word it at the very end actually refers to the cat you mentioned way back at the beginning? Cracking that problem, what they call long-range dependencies, that was the absolute key to unlocking the next level of AI.
Okay, so the main fill-in in our story here is something the paper calls the inherently sequential nature of the older AI models. Basically, they had to process everything one single piece at a time, in order. This created this huge bottleneck. It wasn't just slow, it literally limited their ability to see the bigger picture.
Here's a good way to think about it. Imagine you're trying to read a book, but you're looking through a tiny little tube, so you can only see one word at a time. That's sequential processing. You'd have to try and remember everything that came before, and man, it would be slow, right? Now, imagine you can just look at the whole page at once. Bam! You instantly see how all the words and sentences connect. That's parallel processing. And that's exactly what researchers were dreaming of. All right, so before this big shift in 2017, the top dogs in the AI world were called recurrent neural networks, or RNNs for short. You might have heard of powerful versions like LSTMs. For anything that involves sequences, like, language, these guys were the dominant approach, period. And this really gets to the heart of the problem. See, RNNs were clever, for sure, but they were trapped by that sequential design. They had to process things word by word by word, which made that whole parallel processing thing we just talked about totally impossible. So not only were they slow to train, but, and this is the big one, they really, really struggled to connect words that were far apart. The signal just got lost along the way. And this is where the breakthrough happens. The paper comes along and proposes a model built entirely on something called an attention mechanism. In the author's own words, this allows the model to connect related words without regard to their distance. Suddenly, it didn't matter if two words were right next to each other or 10 sentences apart. The connection could be made instantly. So let's talk about the core idea here, which is called self-attention. It's so cool. Basically, the model looks at a whole sentence, and for every single word, it kind of asks itself, okay, which other words in this exact same sentence are most important for figuring out what I mean? It learns to draw these connections between all the words at the same time, building this incredibly rich map of how the sentence fits together. And this diagram, this is the engine that makes it all happen. It's called scaled dot product attention. Now, don't worry, we're not going to get bogged down in the math. Just think of it like this. For any given word, let's call it the query, the model compares it to all the other words, the keys, to figure out how relevant they are. It gives each one a score. Then it creates a new, super contextualized version of our original word by blending it with the others, the values, based on those scores. It's just a super elegant and crazy efficient way to calculate context. So what did the authors do? They took this incredibly powerful idea of self-attention and they built a whole new architecture around it. They just threw out all those old, slow, sequential layers completely. And this new model, built purely on attention, they called it the transformer. And here it is. Behold, the architecture that changed everything. Over on the left, you've got the encoder stack. Its job is to read and understand the input. On the right, the decoder stack generates the output. And look, you see those multi-head attention blocks all over the place? But you know what you don't see? Any of those old recurrent layers. Nope, it is attention all the way down. I know, that diagram can look a little intense. So let's just break it down into a simple two-step process. First, the encoder. Its job is to read the entire input sentence, let's say an English sentence, all at once. It uses self-attention to build this really deep understanding. Then, the decoder kicks in. It starts generating the output, say the German translation, word by word. But here's the magic. For every single word it creates, it's constantly paying attention to the entire understanding the encoder built. That's how it stays so accurate and context-aware. Okay, so a clever architecture is one thing, right? But the million-dollar question is, did it actually work? Was it better? Because at the end of the day, performance is all that matters. So the researchers put the transformer to the test on a super difficult task, machine translation. And the results were, well, they were staggering. On the standard benchmark for English to German translation, the transformer didn't just beat the best single models out there. It beat the ensembles, which is when you basically team up a bunch of top models to work together. It scored a 28.4, which was a brand new state of the art. Now, a jump of over 2 points on this scale, it might not sound like a lot, but trust me, in the super competitive world of AI research, that is a massive leap. We're not talking about a small, tiny improvement here. This was a fundamental step change. It was proof that this new approach was just flat out superior. But wait, here's the real kicker. It wasn't just better. It was also faster and more efficient. The paper literally says it was more parallelizable and needed significantly less time to train. I mean, their big models set a new record after training for just 3.5 days. This combo, better performance and higher efficiency, that was the holy grail. That's what unlocked the door to training the ginormous models we see everywhere today. And you can imagine the impact of this went way, way beyond just machine translation. The transformer wasn't just another new model. It was a completely new fundamental building block for AI. It gave us this incredibly effective, super scalable way to teach machines the real context and nuance of human language. You know, in their conclusion, the authors wrote this sentence, and honestly, it turned out to be one of the biggest understatements in the history of computer science. That exact architecture they built, that's the T in GPT. It is the literal foundation for pretty much every single large language model and generative AI system that we're all so fascinated by today. So when you boil it all down, a simple, really elegant idea, just letting a model weigh the importance of all its inputs at once, is what finally solved that sequential bottleneck. It unleashed this incredible wave of innovation. It cracked the code on context. Which, leaves us with one last really fascinating question to chew on. What's the next big bottleneck that once it's solved,